Welcome back to the Tutor Wizard. I'm Adrian. Please subscribe right here. Hit the notification bell. We're doing multivariable calculus. Chapter 0 is differential equations. 0.4 is second order differential equations. This lecture, what we're going to do is wrap up second order constant coefficient linear ordinary differential equations, which are non-homogeneous. To do this, what do we need? To find the general solution to one of these things, we need the homogeneous general solution and a particular solution. What we're going to do today is the second method of finding a particular solution to a non-homogeneous second order differential equation called the method of variation of parameters. And we'll do at least one example. Let's do it. For the method of variation of parameters, which is first derived by Lagrange in 1744, what are we doing here? Basically, the idea is we're giving a second order differential equation which is now non-homogeneous. F is not identically 0. What we want is the general solution to this. It turns out we need a homogeneous solution and a particular solution. This method is going to find a particular solution cleverly by using the homogeneous scenario and then varying the parameters C1 and C2 as varying them as functions of x, and that's why they're going to call it variation of parameters. So let's start. Given this non-homogeneous one, we always have an associated homogeneous equation. We just let f equal 0 temporarily. Then from that, in the previous videos, we saw systematically our theorem gives us the general two linearly independent solutions, or the general solution to the homogeneous equation of this form, where y1 and y2 specifically have three different explicit expressions depending on the roots of the characteristic equation ar squared plus br plus c equals 0. So we have the three cases and we can always find y1 and y2. If it's two distinct roots, it's e to the r1x and plus e to the r2x. If they're double, then you add the x in there, and if they're complex conjugates, you get the sine and cosine business. Look at the previous video. Then what we're going to do is we're going to vary c1 and c2, and that's why it's called variation of parameters. We're going to call them v1 of x and v2 of x, and then we're going to solve in a clever system, 2x2 system, for v1 and v2 of x. Those are our unknowns. Let's try that. Therefore, what we're going to do is we're going to guess at a particular solution. Last time with undetermined coefficients, you make a guess based on the form, and then you're like, I have to memorize all and multiply it by x and make all these guesses. Here, we're going to make an entirely different guess, but the work to get there is going to be strange, and we're going to have to integrate along the way. The guess is going to be that we vary the parameters c1 as a function of x and c2 as a function of x, and this is what we're going to guess is the particular solution. And I know you can't see in this, but we've already solved the homogeneous solution, so we know what y1 is explicitly, and we know what y2 are explicitly, and therefore we also know what y1 prime and y2 prime. Those are things given. They'll be constant and fixed in this equation. What we're looking for is v1 and v2. So what Lagrange is trying to do is set up a 2x2 linear system of equations in v1 prime and v2 prime, it turns out. This is going to be the first equation. What do we need now once we have this guess? In undetermined coefficients, we took the first and second derivative, plugged it back into the original non-homogeneous equation, and then solved for all the undetermined coefficients. This time what we're going to do is we have to take the first derivative and the second derivative and then try to find these two equations. This will be the first equation, but we're going to try from the scenario of taking the first and second derivative. We want two equations such that we can solve for v1 and v2, their derivatives actually, and then we'll integrate to get v1 and v2. Therefore, what Lagrange does is, first he takes the first derivative of this, and we get this. I separated them out, so using the product rule of this one, product rule of this one, and then grouping them together like this, you can simplify and I get this expression. When we put this back into the original non-homogeneous second order ODE, it's okay to have second derivatives in y1 and y2, but I don't want, and Lagrange doesn't want, second derivatives of v1 and v2 to appear in these expressions because we don't know what to do with them. So the first restriction we do is we make this whole term equal 0. And that's what Lagrange imposes as the additional requirement to this, because I want to take the derivative of this now to take the second derivative, but I don't want to deal with this because otherwise by the product rule I would get second order derivatives of v1 and v2, and I don't want that. So this thing is 0. So then when I take the derivative, this is just gone, and we have to take the derivative of this thing, and then we'll use the original two equations 1 and equation 2, and we know that y1 and y2 are solutions to the homogeneous equation. So a y1 prime prime plus b y1 prime plus c y1 will be 0, and the same thing for y2, and then those terms will go away and we'll get a second equation for v1 prime and v2 prime, and then we're going to use linear algebra to solve for those guys. First, make this restriction where this whole thing is 0. Now what I'm going to do is take the second derivative of this expression. Let's see what happens. Okay, with our extra assumption that this guy is 0, which Lagrange imposes upon us so that we don't have to get second derivatives of v1 and v2, we're going to take the derivative of this to get y double prime. the particular solution. This one's 0, gone. And then for this one, I use the product rule again, and notice that v1 will be the derivative, and v2 will have a first derivative, but only y1 and y2 get a second order derivative in this case when we make this assumption being 0. Therefore, now I have an expression for the first. This is also 0, so I don't need it in the expression when I put it down here. I have an expression for yp, its first derivative and second derivative. I plug those into the original equation 1. Rewind the tape a few minutes and look at equation 1, the original non-homogeneous equation. Therefore, we're writing that in reverse. F of x was equal to this. Putting those in there and cleaning everything up, I'm going to notice that I have a times v1 y1 prime prime plus b v1 y1 prime plus c v1 y1. Grouping that together, I can pull the v1 out of everything, and then I'm going to get this guy. And then same thing for v2, I can pull the v2 out and I'm going to get this. These are the solutions to the homogeneous equation, because that was specifically the most general solution to the associated homogeneous equation. So those are both equal to 0, and therefore the only thing left is we get f of x is equal to this guy. A is a non-zero constant, otherwise it's not a second order differential equation. So A is not 0, we can divide by A and we get our second equation for our linear system, 2x2 system. What that gives us now is, dividing by A, we get our second equation for, now we have two equations and two unknowns which are linear in v1 prime and v2 prime. Let's recap. Equation 3 was our first one. This restriction being 0 is our first equation. And now we have a second equation, cleverly putting that back in there. Now let's solve that linear 2x2 system in v1 prime and v2 prime. And then once we do that, we're going to have to integrate to get v1 and v2. We're a third of the way there. Now, from equation 3 and equation 4, we have a system of two equations and two unknowns. Those unknowns are v1 prime and v2 prime. Therefore, from Cramer's rule, what we can do with that is, this is the terminology, we call this the Wronskian. The Wronskian is the coefficient matrix, the determinant of the coefficient matrix. So the determinant of that coefficient matrix is this hot mess, y1, y2 prime minus y1 prime, y2. But if you don't want to memorize that formula, it's a whole lot easier to memorize that this hot mess expression is just the determinant of the coefficient matrix when you set that up. We're going to do an example in a second. Then that's the determinant of A, the coefficient matrix, is the Wronskian. It's non-zero because we already know y1 and y2 are linearly independent solutions to the homogeneous equation. That we know. Then what we do to solve Cramer's rule is the determinant of A1 is going to be the matrix obtained by replacing column 1 with this guy. So I put this where y1 and y1 prime would go. Then I compute the determinant, I get this guy. Same thing with A2, I replace the second column of the coefficient matrix with this equals vector. Then we get this guy, and that's why in this v1 has y2, and it was like, well, because you're not memorizing the fact that it's Cramer's rule, and v2 is going to have y1 in the expression. But if you view this as the ratio of this determinant over this determinant, this is clearly the solution for v1 prime. And the ratio of this determinant over this one is this expression. So I've now just got an explicit, unique solution for v1 prime and v2 prime by Cramer's rule, because I know this determinant was non-zero, there has to be a unique solution as the ratio of determinants. This is it, except I didn't want v1 prime and v2 prime, I wanted v1 and v2. So we have to integrate these, and then we're done. Here's variation of parameters. Recap. We guess that we varied the C1, C2 from the homogeneous equation solution, and this is our guess for our particular solution. Then we derived a system of two equations and two unknowns by cleverly manipulating. Our first restriction was that this was 0. Then we plugged it into the original equation and we got this equation. What we do with that now is the Wronskian is non-zero because y1 and y2 are not linearly independent. y1 and y2 are linearly independent, therefore we know that the Wronskian is non-zero. This gives us a unique solution by Cramer's rule. This is the unique solution of v1 prime and v2 prime using Cramer's rule of the ratio of determinants, where those determinants are all containing horrible functions, these hot messes. And if you can't see that this was a ratio of the determinant over determinant, this is hard to memorize for yourself, so it's better to go back and meditate on this and memorize it as the ratio of determinants in Cramer's rule, so then I don't have to memorize these formulas. Then integrating with respect to x finally gives us what we wanted, the unique up to a constant, technically plus c1 and plus c2, but in most cases you can make those 0. Up to the constant we get the unique solutions v1 and v2. Now what we're going to do is an example so that you can actually see how we use all these moving parts, and it's much better to view it as ratio of determinants once they have a bunch of functions. But remember, in this, I know what y1 is, I know what y2 is, I know what the derivative of y2 is, I know what the derivative of y1 is, I know what a is, I know what f is. The only things we don't know are the v1 and the v2s, and we're going to solve for those guys. Let's try this. We're going to find the general solution to the ordinary differential equation y prime prime plus y equals tan of x on the interval negative pi over 2 to pi over 2. Don't worry about the interval, whether it's added or not. They're going to use this to show that my inside function is positive. I can get rid of absolute values in this natural logarithm. But either way, what I should point out before we start is I cannot use undetermined coefficients for this one, because even though I can solve this, the homogeneous part, I can't. This is not one of our forms of our nice non-homogeneous ones in the categories of undetermined coefficients. Therefore, we can't use that technique, and we have to use variation of parameters or keep screaming at the sky with our hands raised. So I'm going to try variation of parameters and see if that works. It does. What do I need to do? First of all, one, I would immediately make tan 0, which is good, and solve the homogeneous equation. We need the two linearly independent solutions to the homogeneous equation, and we get those from the theorem depending on whether the roots are two distinct roots, a double real root, or two complex conjugates. I can see that it's r squared plus 1, which is the classic one. This is going to be two complex conjugates. Y prime prime plus y equals 0. Start with the homogeneous equation. That immediately gives me the characteristic or auxiliary equation r squared plus 1 equals 0. Solving that, I get r1, 2 is equal to plus or minus I, which is actually 0 plus or minus 1 times I. What that technically tells me is alpha is 0 and beta is 1 in the general theorem. Then what I know is, because I had two complex roots, I can immediately use the homogeneous theorem to tell me that the general solution to the homogeneous equation with the two linearly independent solutions is c1 y1 of x plus c2 y2 of x, where what is that going to be? Because it was complex conjugates, this will be c1 e to the 0, which is a 1, times cos of 1x, plus c2 e to the 0, which is 1 times sine of 1x. Beta x is usually what we do, alpha beta. Therefore, this is our homogeneous solution. Therefore, now you can see this is y1 and this is y2. I have them in the equation. Once we actually do an example, I've got them. This says y1 is cos x and y2 is sine x. Therefore, you can immediately take the derivatives, but we're going to put all of this in together. Step 2. What I'm going to do is, once I have the homogeneous solution, I'm going to find their first derivatives, then find the Wronskian, then play this game of the Cramer's rule. I'll set up the equation, but I need the Wronskian first. Therefore, y1 prime of x is equal to negative sine x. Oh, I see something happening. And then y2 prime is going to be cos x. Therefore, the Wronskian w of y1, y2. Wronski is a Polish mathematician, that's why it's called a Wronskian. Wronski says this is going to be the determinant of y1, y2, y1 prime, y2 prime, which in our case is going to be cos x sine x negative sine x cos x, which is rotation through x counterclockwise. The determinant of that is equal to cos squared x plus sine squared x, which is going to go away in our calculation. Good. We have to divide by Wronskian, remember. Good. I gave myself one where it goes away, not you. Next, what do I do? Now that I have the Wronskian, let's set up the system of equations and find v1 prime and v2 prime, and then we'll integrate. Okay, 3, what we're going to do is, now let's recap what we've done. I found the homogeneous part, y1 and y2. Then what we did is take their first derivatives, and I compute the Wronskian. In this case, it was a nice 1. Also, when I look at our original ODE, a is 1, the coefficient of y prime prime, and f of x, our non-homogeneous, is this guy tan. So now I have those 3 things. Then what it says is v1 you get by integrating that ratio of determinants, and v2 is you get by integrating that ratio of determinants. Therefore, when I put that in there, v1 is negative 1 over a, f times y2 over the Wronskian. Integrated. In our case, that was negative 1 over a was 1, f is tan, y2 is sine x, and the Wronskian was 1. And now integrating that, what I get is, I have to be clever a little bit, this gives me negative the integral of sine squared x over cos x dx. When you're stuck, the first mantra is turn everything into sine and cosine when you have trig. So I did tan is sine over cos. Therefore, when you're stuck with sine squared, use the Pythagorean identity. Sine squared is 1 minus cos squared. This is negative the integral of 1 minus cos squared x over cos x dx. I'm going to distribute the negative in and then simplify this. This is secant negative and positive cos squared over cos is cos. what? This. You get cos x minus secant x dx when I simplify. Therefore, the antiderivative of that is going to be sine x minus the natural log of the absolute value of secant x plus tan x plus c1. And then technically what they're doing here is, I shouldn't even do it, but you can draw if you want the absolute values because we're in the interval. X is in the interval negative pi over 2 to pi over 2, and therefore secant, cos is positive in there, and so therefore, and so is tan in that interval. But whenever you're unsure, just leave the absolute values in there. And this gives us, what was that? V1 of x. Then what I'm going to do is integrate this. V2 is going to be, what is that going to give me? This time, this is the integral of sine x over cos x times cos x dx. Cancel, cancel. This is the integral of sine, the integral symbol is an s. Make it a little bit fancier. The integral of sine x. The integral of sine x dx is what? Negative cos x plus c2. For simplicity, because we have this family, I'm going to let this guy equal 0 and this guy equals 0. And then what are we going to do? Let's clean that up. Technically what we have now is v2 of x and v1 of x. And then forest for the trees again. Everyone gets so excited because we have those two. You're like, I'm done. No, we wanted the particular solution. We now have to put these guys multiplied by these guys and simplify a little bit. And then we have the particular solution we were looking for. And then we're still not done. Read the question. It said find the general solution, which is the linear combination of the homogeneous and the particular. Right now I'm finding the particular solution using the method of variation of parameters. And then the general solution is going to be the homogeneous plus this particular solution. 2 more steps. All right, to summarize, basically step 4 is going to be, we now have the particular solution. The particular solution is v1 times y1, v2 times y2. You work so hard cutting down the trees of finding v1 and v2. You're like, yeah, that's not what we were looking for. That only gives us the particular solution, and you still have to build it. Simplifying, distributing this in, I see I have sine x, cos x, and then I have negative sine x, cos x, so those are going to cancel off, and then I'm just going to be left with this term. That means y particular is this guy. We're still not done. That gave us the particular solution. We now have the homogeneous solution and the particular solution. Therefore, the general solution to this equation for x in the interval negative pi over 2 to pi over 2 is given explicitly by y of x, which is the linear combination of the homogeneous solution and the particular solution, which is the 2 linearly independent functions we already have, plus the particular solution. Therefore, in our case, our general solution is c1y1 plus c2y2 plus the particular solution. That is the general solution to this differential equation. Please subscribe right here, hit the notification bell. I'll see you next time. My 2 system. That one's a wasp. Wasp! Don't try to just grab that guy.